Swayam Prabha. Digital India. Educated India.
So in the last class, we have discussed about different circuits using op-amp. For example, op-amp differentiator, op-amp integrator, right? Log amplifier, anti-log amplifier, all this stuff, right? So today we are going to discuss another uh, type of amplifier using op-amp, which is called the difference amplifier, right? So let us start. Okay. Difference amplifier. So the circuit diagram of this difference amplifier is like this. We have these two terminals of this op amps. In this inverting terminal, we have connected two resistors like this. One is here R1, R2 as in feedback resistor, negative feedback, you know that, right? Here we have also one resistor connected with this non-inverting terminal, which is R3, and here we have another resistor which is R4, right? And we have two signals here, not one signal, right? One signal has been applied to this inverting terminal and the other signal has been applied to this non-inverting terminal, and this is the output. Fine. So this difference amplifier is an amplifier which amplifies only the difference between these two input signals, and if there is some common part between these two inputs, right, then this amplifier is expected to reject that signal. So common part will be rejected, it's expected, and the difference part between these two signals is expected to get amplified by this amplifier, right? So let us do step-by-step analysis of this difference amplifier, and let us see what is the expression of this output voltage in terms of this R1, R2, R3 and R4, right? So how to start? First thing is that you can see here, like there are two signal sources, V1 and V2. So probably we can use the superposition, right? Then we can analyze one signal at a time, keeping the other signal as ground, right, or zero, right? So for example, if we consider like first this for this V1, okay, when we applied only this V1, so at that time this is grounded, right? This is grounded, right? And if this is grounded, you know that there is no current flowing through this op amp or coming out of this op amp, so the voltage drop across this R3 or R4 is basically zero. So then this potential is also zero, right? So then you can see this part, the remaining part of this amplifier is nothing but, and it is nothing but an inverting amplifier, right? So, and for this inverting amplifier, the gain, this input is V1. So what will be the output for V1? This output is, or we let us say VO1, because to denote the output corresponding to for this input V1, this will be equal to minus of R2 by R1 into this input voltage, right? This is Vi, isn't it? Right. Now, second case, when V2 is applied. So when only V2 is applied, right, then this V1, in place of V1, we have to ground it, right? Isn't it? Superposition. So when V2 is applied, you can see this is grounded, right? And we have applied here this V2. So now this potential is no longer V0, but you can use one voltage division rule to find what is the potential here, right? And let us say that this potential is V in. Then what is this V in? We can write V in terms of this V2 and this R3 and R4, right? Simple voltage division. R3 plus R4, isn't it? Right. Because now if you ground it and you have applied this one, and if the here the input is this V in, right, then obviously we can find what is the output voltage V out. Then what will be the output voltage V out? This is an non-inverting amplifier, so the gain will be 1 plus this R2 by R1, R2 by R1 into the input. What is the input here? It is nothing but this V in, right? So then let me write it, this R2 and R1. What is V in? V in is nothing but this one, right? So maybe we can write this one before into V2, right? So this is the output voltage when this V2 is been applied. So let us also like this point it out by this V naught 2, right? Output voltage for this input voltage 2, V2. Okay. Then what is the total output? Total output is nothing but the algebraic sum of these two, V naught 1 and V naught 2, right? So what is V naught 2? So this is this one. So it is 1 plus R2 by R1. If we divide both numerator and denominator by here this R3, then we will get something like this, 1 plus R4 by R3 into V2. We are just dividing here by I3, by here also R3, right? So, and what is V01? V01 is this one. So it is minus R2 by R1 into V1, isn't it? Right. Now, if this R4 by R3 is equal to R2 by R1, then see what happens. If this R4 by R3 is equal to R2 by R1, so this become now 1 plus R2 by R1. So this 1 plus R2 by R1, here also 1 plus R2 by R1, these two cancel out, right? And here R4 by R3, this R4 by R3 can be written in terms of R2 by R1, right? So this term now becomes R2 by R1 into V2 minus here it is R2 by R1 into V1. Now if we take these two part as, right, better simplify this one, right? Then what you can see it here, that the output voltage is equal to R2 by R1 into V2 minus V1, right? Right. And if this V1 is equal to V2, that means the same input is being applied to this terminal, to this inverting terminal and this non-inverting terminal, then the output voltage V output is expected to be 0, right? So that means if common signal is being applied between these two terminals, then the output is expected to be 0. If they are not same, if this V1 is not equal to V2, right, then these two signals are the different signal, and for that we have achieved one gain for this amplifier, and this gain is this one. So this is the gain, right? Because this is the difference, right? This is the output voltage, so obviously this is the gain. And what type of gain is this? This is nothing but the differential gain, right? This is the differential gain, so it is called this AD. Remember, it is different from that AOD because it is the closed loop differential gain. What AOD we have discussed at the beginning of our this op-amp course, right? There this AOD was the open loop gain, open loop differential gain, but this one is the closed loop differential gain, right? So is that part clear to you? Okay. So you understand that like if this condition is satisfied, then for V1 equal to V2 we are getting output equal to 0, right? But what will happen? Okay, what will happen if R4 by R3 is not equal to R2 by R1, right? And but suppose V1 is equal to V2. In that case, so definitely from this equation, okay, you can comment, then in that case the output will not be equal to 0, right? So you can see here the same signal is been applied, but still the output of this difference amplifier is not equal to 0. So this V1 and V2, these two signal in that case is called the common mode input signal. Okay, this V1 and V2 are called this common mode input signal, right? And it is denoted by this V of Cm symbol, right? Maybe we will go to the next page and continue our discussion. So this V of Cm, that is the common mode input signal, okay, this is defined as this V1 plus V2 by 2, right? So if this output is not equal to 0, so that means you can write this output in that case is equal to some gain, right? Some gain into this signal, common mode signal V of Cm, right? So what is this gain? This particular gain is called the common mode gain. Common mode gain, and we denote it by the symbol this ACM, right? But do you expect from any op-amp this common mode gain? No. Ideally we expect the common mode gain to be equal to 0. But in practical op-amp, this common mode gain do exist. Even though this value is maybe lower, but it does exist. Fine. So you understand then what is this A of Cm? A of Cm is nothing but the output voltage by the common mode input voltage. So in this regard, regarding this common mode gain and differential mode gain, because we want that op-amp for this difference amplifier to amplify only the difference, but we can see that for certain cases we do also have this common mode gain. In this context, one figure of merit has been introduced, and this particular figure of merit is known as common mode rejection ratio. Common mode rejection ratio, or in short it is written as CMRR, common mode rejection ratio. And the CMRR, this is defined as the ratio of differential gain by common mode gain, and generally we keep it under the mod because some cases this some gain might be negative, right? Right. And what is the value that you expect of this CMRR? So CMRR value is expected to be very high, right? CMRR value is expected to be very high, right? And many cases, as this is a very high value, the CMRR is represented in terms of in dB scale, right? So CMRR in dB scale, it's defined as 20 log of mod of AD by mod of ACM, right? Here the 20 will come because this AD and ACM are the voltage gains, right? So remember that CMRR in dB can be represented in this way. So is this CMRR part is clear to you? Maybe in the next page we can discuss one circuit where I think we can illustrate the CMRR concept and this common mode gain concept in a better way. So let us go to the next page. Yeah, here suppose we have a circuit like the difference amplifier circuit. Okay, let me draw the circuit first, then negative, positive. This is the output, this is R2, this is R1. Here we have applied V1. Here we have R4, we have R3 here, we have V2 here, right? In earlier case we have seen that this output voltage will be equal to 0 if V1 equal to V2 and R2 by R1 is equal to R4 by R3, right? If that condition satisfies, right? But here for this particular case intentionally we are assuming that here this R2 by R1 this is equal to 10 and this R4 by R3 this ratio is 11. So obviously you can see this R4 this R2 by R1 and R4 by R3 this ratio is not same, right? Then what will be the output? This output we have seen that in the last page. So what is the output? We can write the expression of output like this: 1 plus R2 by R1, the same thing what we have derived last page, R4 by R3, 1 plus R4 by R3 into this V2 minus R2 by R1 into V1, right? Now we know the ratio of these resistances, so let us substitute that. So here this value is 10, this value is R4 by R3 is 11, here it is 1 plus 11, right? Okay, and here we have this V2 minus, here we have this value again 10, so this is 10 V1, right? So this is V out, so this V out, if you just do the calculation here, 0833, this V2 minus this 10 V1, right? So what you can see here now, even if this V1 equal to V2, right, the output is not equal to 0. So please take a note here, output is not equal to 0 even if V1 is equal to V2 for this case, right? So that means for this difference amplifier some common gain exists, right? So we need to find that, and we have to also find what is the CMR, okay, for this particular circuit configuration, right? Okay, now what we have seen in the last page is that we have two types of signal. One is the difference signal, that is nothing but the difference between these two, V2 minus V1, and we have a common mode signal. We have defined this common mode signal like this, V1 plus V2 by 2, right? So this is the difference mode input, difference mode input, and this one is the common mode input. Fine, we already know that, right? Okay, now if you know these two things, right, then can you not write this V1 and V2, this V1 and V2 in terms of this VD and VCM like this. See here. Can we not write V1 equal to VCM minus VD by 2 and this V2 is equal to V of CM plus VD by 2. Please check, because if you now make this V2 minus V1, so this CM V of CM VMCM cancels, VD by 2 plus VD by 2, that becomes this VD, right? Similarly, if you take this V1 plus V2 by 2, then you see these two cancels, this 2 VCM by 2, it is V of CM, right? So we can write this V1 and V2 in terms of this V of CM and VD, isn't it? Right. So if you agree that we can write it like this, then probably here this equation, okay, where we have seen V output in terms of V2 and V1, we can replace this V2 with this and this V1 with this, so that we have an here relation between output and this difference mode input and this common mode input voltage, right? So let us do that. So it is basically 10.0833 into this V2 is V of Cm plus Vd by 2, it is minus 10 into V of Cm minus Vd by 2, isn't it? Okay. Now if we just do a bit simplify so that all VCM and Vd come together, then it should come like this: 4 2 of Vd plus 0.0833 of VCM, right? So if you now see this equation carefully, then you will notice that this equation relates this output voltage with this difference mode input and this common mode input, right? So this output is equal to this difference mode gain into this difference mode input, right? So then basically this value is nothing but the AD, difference mode gain, and this value is nothing but this common mode gain, which is A of Cm, right? So now if we write this equation like this, then from this equation only tells us that the value of AD or this difference mode gain is this, and the value of common mode gain is this. So if you now know this value of AD and value of A of Cm, and obviously you can see from this equation that the value of this AD is much higher than that of this A of Cm, right? So if you want to now find the CMRR, right, then it's basically this 10.042 divided by 0.0833. You have to just take a calculate it and find the value of this CMRR, right? Remember we have discussed this, that CMRR is generally represented in dB. So if you want to take it in dB, so it will be this 20 log of this 10.042 by 0.0833, right? And here all are positive, so we are not giving this mod, otherwise you have to give this mod. So if you estimate this, it should come like this dB, right? So you can see here that the CMRR or the common mode rejection ratio for this difference amplifier is actually pretty high, right, which is 41.6 dB, right? And in general, for this typical CMRR values, remember that for your information, lies in between this 80 to 100 dB. So let me write it here. This typical CMRR is between 80 to 100 dB, right? Remember this value. Okay. So as expected, the CMRR value has to be as high as possible, right? So I hope with this the concept of this common mode gain and the concept of this CMRR is clear to you now? Okay. Now, do you remember that other than this different amplification, another term was quite important to us, that was the input resistance of any amplifier, right? So, what would be the input resistance of this amplifier? Can you comment on that? What would be the input resistance for this amplifier? For ideal amplifier, the input impedance is infinite, right? But what would be the value of input impedance for this case, right? So here not much space is available, so let us go to the next page and do that. So maybe we will quickly draw the circuit, difference amplifier circuit again. So this is one resistor, here we have another resistor, we have one resistor here, we have one another resistor here, right? And let us say for this case it is R1 R2, and this one was also same, the ratio is same, means R2 by R1 equal to R3 by R4 by R3. Okay, that ratio is satisfied, right? In that case it will be also R1, right? And this will be also R2, right? And this is the output voltage, right? So if so, like this, then if you have to estimate what is the input resistance, how do you find the input resistance? There are, in some cases by only inspection you can find, right? But in other cases also, what you can do, the one simple way would be just to connect one voltage source. Okay, connect one known voltage source here, okay, and find what is the current, okay, and what is the current that is flowing through the from this voltage source. So if you know the voltage, if you know the current, then you can estimate what is the resistance. It is nothing but this V by I, right? So let us do that. Okay, but before we proceed, one thing we should notice here is that, right, this op amp is an ideal op amp, right? This op amp is an ideal op amp. So if this is an ideal op amp, then the virtual short concept applies, right? And due to virtual short, this potential and this potential will be the same. So that way we can consider that this two potential is actually shorted, even though it is virtual short, right? So in that case, if you want to quickly estimate what is the current, then this circuit, you can see it here. This is V, this is I, this is R1. So if this current is I1, then the same current has to come back to this, right, from here, right? So that way, if you look from here, then you can write this V, though this voltage is equal to this R1 into I plus, because here it is plus minus, here it is plus minus, because current is flowing like this. So here also R1 into I. So that way this V by R, which is nothing but the input resistance, will comes out to be 2 R1, right? So you can see here the input impedance, right? The input, better to say that input resistance of this amplifier is not infinite as that of this ideal op amp, but rather it is dependent on the resistances that we are using. So for this particular case, it is dependent on the value of this R1, right? So this R1 is some finite value, but we have discussed it earlier. Generally, what we want the input impedance to be as high as possible, right? So that part is not happening in case of this difference amplifier. So what can we do? Is there some way that you can do? Maybe one of you, maybe some of you can suggest, okay, why are you doing like this? So you can just add one buffer here, right? Add one other buffer here, right? Yeah, you can do that. You can use an buffer here, but that will give rise to other complications. Okay, so is there any other way by which you can do that? Okay, and one more thing, important thing is that, see here, uh, or maybe I will draw this circuit bit once more so that it would be easier for you to understand. See here, in earlier case we have said that this is R2, this is R1, this is V1, right? This is R3 and this is R4. This is V2, right? And this is nothing but, this circuit is nothing but the special case of this circuit only, where this ratio R2 by R1 is equal to R4 by R3, right? And this is the output. So what is the gain of this? If this R4 by R3 is equal to this, we have just now derived, right? The gain would be equal to what? R2 by R1, right? So this output voltage, okay, it depends on the value of this R2 by R1. Suppose now you are planning to change the gain, increase the gain, then you have to change this R2, right? You change this R2, but whenever you are changing this R2, to keep this condition intact, you need to also change this R4. So that means simultaneously the two resistance value you have to change, right? So one thing is that the input impedance is not high for this difference amplifier. Other thing is that at other shortcoming is that if you have to increase the gain, so the resistance value, two resistance values actually you have to change, isn't it? So is there any way by which we can actually solve this problem? The answer is yes. So for that we can use another special type of amplifier which is called the instrumentation amplifier. So let us do that here. So let me write it first. Instrumentation amplifier. Fine. So how does this instrumentation amplifier looks like? Okay, let us draw the circuit. It is easy only. So we have here two op amps, right? And to this inverting non-inverting terminal, we are applying this one of the signal supply, that is V1 or signal you can say, right? And this is obviously one non-inverting amplifier, right? So this should be the negative feedback, okay, connected with a resistance R2. Here this resistance R2 is again connected with another resistance which is R1, right? And here we have another op amp. This is negative, this is positive. Here we have the other signal source, that is V2, applied to this non-inverting terminal of this op amp. So again this is a non-inverting amplifier, this part, right? So we should have one feedback resistor, negative feedback, right? And say this resistance is also R2, right? And these two are coming out, and so obviously output voltage you have to indicate. So say this output voltage is V01 and this output voltage, intermediate output voltage, is V02, this two, okay? And after that actually we are connecting two resistances. One is R3, both are R3, right? And through which R3 and R3 we are feeding this to this op amp, right? Which is nothing, if you look this part, then you will see that this part is nothing but the difference amplifier, right? If you look now this part, this is what? This is nothing but the difference amplifier, right? So we have considered the ratio that R4 by R3 means this ratio of these two resistances is equal to ratio of these two resistances, right? And this is the final output, right? So if you now just see the overall circuit here, so we have in here non-inverting amplifier, we have another non-inverting amplifier, this one. Output of this two non-inverting amplifier is connected with this difference amplifier, and then let's analyze what is the output voltage here. Okay, so for that, suppose if some current, okay, is flowing through this I2, we will try to find out what is this current. This some current, suppose this is I1, right? This current is flowing through this, fine, right? You know, no current can flow through or in or out of this op amp terminal, so this current is 0. So if this is I1 current, then the same I1 current has to flow through this, right? Similarly, here no current can coincide to this op amp, so this same I1 current should flow to this resistance R2, right? I think you will agree with me on this, right? Now these two op amps, this op amp and this op amp, are again ideal op amp, so we can use the virtual short concept. So that means the potential between these two and the potential between these two are basically same, right? So using this virtual short concept, what we can write, this potential is also V1 and this potential V2, right? So basically here this is V2 and this is nothing but V1, right? So you see then what is this V1? V1 is the current flowing through resistor R1, and the potential drop across this R1 is V1 minus V2. Then I can write obviously I1 equal to this V1 minus V2 by R1. Can I not? Yes. So if we can write this, okay, then we know what is the value of this. What about this V not 1? This intermediate output here, can you comment on that? See, we know the voltage here, this is V1, because V1 is the supply, we know that, right? Or signal, that is a known, right? And you know the current, I1 current is flowing through this, which we also, I1 also represented here in terms of V1 and V2 and R1, known quantity, right? So if the current is flowing through this, so there will be voltage drop here. So you know this voltage, you know this voltage drop, then you can find this voltage or this voltage. So this V not 1, right, we can estimate from this I1 R2, right? This is R2 drop. Do you agree with me? Right. Now here this is V of O2. Similarly, here it is V2 and the current is flowing like this. So it is V2 minus of I1 into R2, right? So it is V2 minus of I1 R2, right? Okay. Now you see we know the value of this I1, so we can put the value of I1. Similarly, we can put the value of I1 here, both in, then we have a relation between this V01 and we can represent this V01 in terms of this V1, V2 and the resistances. Same thing we can do for this VO2, right? So let us do that. Maybe I will pick another color, or let us say green. So to save some space, I am writing it from here. So it is V1 plus I1 R2, this one, right? And you know the value of I1, so let me write that. It is V1 minus V2 by R1 into R2, right? What is this or what is this? Okay, you can split it, to make it, because we have to then, and do a summation here, right? Or make a difference here to find this output, right? Okay, let's do step by step. So what is this VO2? VO2 is nothing but V2 minus I1 R2. So you can see it from here. So what is this V2? V2 is same as this. I1 is V1 minus V2 by R1 into R2, isn't it? Right? Okay. If it is you have understood this part, then tell me like what will be the output voltage here, final output voltage. How can you find it? It's not difficult, because now you know what is the input voltage to this difference amplifier, right? If you know the input voltage to a difference amplifier, today only we have learned how to find the gain of this difference amplifier, right? If the inputs are known. So the output voltage is R4 by R3 into, you remember, it is this voltage minus this voltage plus minus this one. Invert the voltage applied at this non-inverting terminal minus the voltage applied at this inverting terminal, right? So that way it is VO2 minus VO1, right? Okay. So it is straightforward now, right? So we have an relation between V output and this two, and this V output 2, V output 1, V output 1 and V output 2, both we can write in terms of these input voltages and resistances, isn't it? So I request you to please put the values here. This R4 by R3, for example, this V1 plus this V1 by R1 into R2 minus V2 R2 by R1. Okay, this is this part, right? Then minus of this other part, right? This VO2. So please do it. So if you calculate the total part here, okay, then finally what you will get is that V output is equal to R4 by R3 into V2 minus V1 into 1 plus 2 R2 by R1. Right, it is not difficult, right? Or do you want me to do it? Okay, maybe then we can do it. It will not take much time. So it is V2. We are just have to be careful on the sign. So it is minus, so it become plus, right? So it is V1 R2 by R1, right? Then it is minus or plus, then again here minus, so it will become again minus. It is V2 into R2 by R1, right? So you can see here this V2 minus V1 term will be there. I think I just made a small mistake here. So because it is VO2 minus VO1, so I have to put this VO2 first, right? So maybe I will correct it. Just a minute. Yeah, so it is VO2. So VO2 is this one, right? V1 into R2 by R1, all right? Then plus, right, V2 R2 by R1. Then we have a minus here, so all these terms will now become minus, right? This is V1 into R2 by R1, right? This minus, now this become plus. This is V2 R2 by R1, right? Whole will be under in the bracket, right? So please remember that. So you can see it here, like from here, like you have this V2 minus V1 term, so V2 minus V1 term, and you can see this is negative of R2 by R1, this, so 2 times, right? That basically constitute this R2 by R1, this one term, and again you can see here plus this term, so plus of V2 this term, so that basically gives V2 minus V1 into this part, right? So is this part clear to you now? Okay, so if this part is clear to you, then from here few observation is that, first, regarding the gain, if you have to suppose change the gain of this amplifier, then what you have to do? See here, gain is dependent on this, but see, gain is also dependent on the value of this R1, right, which is this resistance. So if you now change only the value of this R1, then the gain of this total instrumentation amplifier, you can actually control the gain of this instrumentation amplifier by changing only one resistor, by only the value of this one resistor, right? Or maybe you can also think of, instead of this resistor, you can use a potentiometer, right? So if you have a potentiometer, now if you now keep on changing this R1, so your this gain of this amplifier will also change, right? Because what is gain here? Gain is so you remember, this is the differential input. So the gain is R4 by R3 into this 1 plus 2R2 by R1 term. This is the gain, isn't it? So that issue is been solved, right? In earlier case, you have to seen that if you have to change the gain, then you have to change simultaneously two resistance as well. That issue is not here. But what about the input resistance? See, this here, this is one of the input, right? This input is directly connected to the ideal op amp input, no in between, no resistance, right? So you know that ideal op amp input resistance is very high, so ideally infinite. So that way the input impedance is infinite. So same thing is here. So the input impedance is now infinite. You remember when we are using only the difference amplifier, then the input resistance was coming to be like the 2 of this resistance value. So 2 of R3 for this case, right? But now for this instrumentation amplifier, the input resistance is coming to be infinite, very high, right? So I hope this part is clear to you.